What if I told you that right now, at this very moment, something humans created is farther from Earth than any physical object has ever traveled? And it's still sending us messages, still working, still revealing secrets about reality itself that are rewriting everything we thought we knew about existence. That's Voyager 1. And what it's discovered at the edge of our solar system will absolutely shatter your understanding of where we are in the universe. But here's the mind-blowing part, and I mean this literally. Voyager is now so far away that it takes light 16 hours to receive a message from it. 16 hours. Think about that. You send a command, and you wait 8 hours for it to arrive. Then, 8 more hours for the response. We're communicating with our own spacecraft across a gulf so vast that human comprehension starts to break down. Welcome to a journey that will change how you see your place in the cosmos. Before we go any deeper, I need to know, where are you watching this from? Drop your country in the comments. And more importantly, hit that subscribe button, because we're about to explore the most extreme frontier humanity has ever touched. What time is it where you are right now? Tell me that too. Because you're about to realize that time, space, and distance means something completely different than you've ever imagined. Let's establish what we're actually talking about here. Voyager 1 was launched on September 5, 1977. That's 47 years ago. Nearly half a century. It was designed to study Jupiter and Saturn up close, take some pictures, gather some data, and then honestly, we expected it to shut down and become space debris. Instead, it became humanity's greatest achievement. And I don't use that phrase lightly. Here's the first thing that will reshape your thinking. Voyager 1 has traveled 14.5 billion miles from Earth. Let me put that in perspective, because the numbers are so large they lose meaning. If you drove a car at 60 miles per hour, non-stop, without sleeping, without stopping, it would take you 27 million years to travel that distance. The entire recorded history of human civilization is only about 5,000 years old. You'd need 5,400 lifespans of recorded human history just to drive there. And Voyager got there in less than 50 years. The reason this is even possible comes from something called the Grand Tour rare alignment of planets that happens roughly every 176 years. In the 1970s, that alignment was happening. NASA scientists, led by Carl Sagan and the brilliant trajectory engineer Gary Flandreau, realized we had a window. A single window. If we didn't launch then, humanity would have to wait until 2153 to get another chance at visiting the outer planets. Think of it like this. Imagine you're planning a road trip across continents, and you discover that if you leave on a specific date, you can use currents and wind patterns to make the journey effortless. But if you miss that date, the next opportunity is 176 years away. That's the scale of what we're talking about. Voyager wasn't just exploring. It was executing the most complex gravitational ballet ever attempted. It used the gravity of each planet like a slingshot. Jupiter's gravity accelerated it toward Saturn. Saturn's gravity slung it toward Uranus, and Uranus flung it toward Neptune. Each planetary encounter multiplied Voyager's speed. By the time it passed Neptune in 1989, it was traveling at 40,000 miles per hour. That speed, that acceleration, that achievement, most people have never heard of it. And here's where the first mind-blown moment hits. Voyager 1 is still accelerating. Not because of rockets firing. It's accelerating because the sun's gravity is still pulling it backward, even as it moves forward. The net effect? It's being pulled away from the sun so powerfully that it's actually speeding up relative to the rest of the solar system. We built something so elegant, so perfectly designed, that the laws of physics themselves are still pushing it onward toward the infinite dark. But this is just the foundation. The real discoveries, the ones that rewire how we understand reality, those come next. Stay with me. Most people think the solar system ends with Neptune, or maybe Pluto, if you're nostalgic. But here's the shocking truth. The solar system is approximately 100,000 times larger than that. I'm talking about something called the Oort cloud. Imagine the Sun at the center. Around it, we have the planets Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. That's the solar system everyone learns about in school. But surrounding all of that, like a vast spherical shell of cosmic debris, is the Oort cloud. A shell of frozen object-CC bodies, comets, remnants from the Sun's formation, that stretches almost 100,000 astronomical units from the Sun. 1 is the distance from Earth to the Sun. So we're talking about 100,000 times that distance in all directions. Think of it like this. If the solar system we know is a marble sitting on a table, the Oort cloud is a transparent sphere the size of a football stadium surrounding that marble. The marble is just the core. Everything else is mostly empty space and distant ice. Voyager 1 has been traveling through this region since the 1980s, and what it's detecting there is fundamentally changing how we understand what a solar system actually is. In August 2012, then mark this date because it's crucial, Voyager 1 crossed something called the Heliopause. This is the boundary where the Sun's influence ends and the interstellar medium begins. The Sun sends out a constant stream of charged particles called the solar wind. This wind pushes outward in all directions. Eventually, billions of miles away, it meets the pressure of the interstellar medium, the cosmic wind blowing from other stars, from the broader galaxy. Right at that boundary, there's a collision of forces. That's the Heliopause. Voyager's instruments detected the precise moment this happened. The solar wind pressure suddenly dropped. The density of the interstellar medium suddenly increased. For the first time in human history, we had direct physical evidence of leaving the Sun's domain. Dr. Ed Stone, the mission's chief scientist, and this man has dedicated 50 years of his life to Voyager, announced this discovery. And he said something that perfectly captures the significance. The Voyagers have taken us to the edge of the Sun's domain, to a place where the Sun's influence ends and the galaxy's begins. But here's what will absolutely blow your mind. The Heliopause isn't a solid boundary. It's not like crossing a line on the ground. Instead, Voyager's data showed that it's this turbulent, chaotic region filled with waves of particles and fluctuating magnetic fields. It's more like crossing a threshold between two raging rivers than stepping across a marked line. The boundary is alive. It moves, it breathes. It's more complex than we ever predicted. And Voyager is still in that region, still sending back data about what this transition zone is actually like. Here's the part that creates cognitive dissonance. When Voyager crossed the Heliopause, scientists expected the cosmic ray measurements to dramatically increase. Cosmic rays, high-energy particles from throughout the galaxy, are partially blocked by the Sun's magnetic field. Once you leave that protection, you should get blasted with radiation. And the data did show an increase, but not the increase we expected. It was about 3 times lower than theoretical models predicted. This means something in our understanding of how cosmic rays behave or how the Sun's magnetic field works is incomplete. Voyager revealed an inconsistency between theory and reality. And that inconsistency is driving current research right now. Think of it like discovering that the shield protecting a castle is much stronger than everyone thought. Now, physicists are scrambling to figure out why. The universe is constantly surprising us with its complexity, and Voyager hasn't even left the solar system yet. Scientists estimate it will take about 30,000 years for Voyager 1 to reach the outer edge of the Oort cloud. 30,000 years. That means this spacecraft will still be transmitting data long after human civilization. As we know, it has fundamentally transformed beyond recognition. Here's your engagement moment. In the comments below, tell me if you could send a message to Voyager right now. What would you want it to tell the universe about humanity? Think about that while we dive deeper. This is where the story transforms from pure science into something profoundly human. Something that will reshape how you think about your existence. In 1977, Carl Sagan led a team to create something unlike anything humanity had ever made. They assembled a golden phonograph recorder, an actual record, and filled it with sounds and images representing life on Earth. The golden record, it contains 115 images, greetings in 55 languages, music from around the world, sounds of earth, wind, rain, animals, scientific diagrams, mathematical formulas, a message from the UN Secretary General, Beethoven Chuck Berry, an Indian raga, Egyptian music from 2000 BCE, and now, attached to Voyager 1, that record is hurtling through space at 40,000 miles per hour toward infinity. But here's the mind-blowing part. We have almost no chance of it ever being found. Let me explain why. The nearest star system is Alpha Centauri, 4.37 light-years away. At Voyager's current speed, it will take 73,000 years to reach that star system. And even then, it won't come close to any planets. The chances of it ever encountering alien intelligence are infinitesimally small. So why did we create it? Carl Sagan gave the answer, and it fundamentally reframes what this mission is about. He said, "This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours." It's not really a message for aliens, it's a message for ourselves. It's humanity declaring, this is who we are, this is what we value, this is what we created, this is the diversity of our world, and we've sent it to the eternal dark with the faintest hope that someday, someone, somewhere, might hear our voice echoing through the cosmos. Think of it like this. Imagine writing a message on a piece of paper and placing it in a bottle. You throw it into the ocean, knowing the chances of anyone finding it are virtually zero. But the act of creating it, of declaring something about yourself and your world, that matters. It makes a statement about what you believe your existence means. That's what Voyager is. On board that record is a photograph of Earth taken by Voyager 1 itself in 1990, that famous image called Pale Blue Dot. From a distance of 3.7 billion miles away, Earth appears as a single pixel of light. One tiny blue speck floating in the vastness of space. Carl Sagan wrote the most profound meditation on that image. From this distant vantage point, the Earth might not seem of any particular interest, but for us, it's different. Consider again that dot. That's home, that's us. Everything that has ever happened, every human who has ever lived there on a mote of dust suspended in a sunbeam. Every war, every scientific discovery, every love story, every song ever written, every moment of brilliance and suffering in human history. All of it happened on that pixel. The profound truth that Voyager revealed, not through instruments, but through perspective, is that from the edge of the solar system, human significance appears infinitesimal. But here's the paradox. The fact that we can comprehend that we can build machines to journey to the edge of forever and understand what we see there. That demonstrates that human consciousness is extraordinary. We are the universe, becoming aware of itself, and the golden record is evidence of that awareness. Here's your second mind-blown moment. Every person alive today, everyone watching this video, your voice is out there. Not specifically your voice, but representatives of humanity. your music, your science, your existence. You are part of this message humanity sent to eternity. You are encoded in the cosmos in a way that will literally outlast human civilization. After Voyager crossed the Heliopause in 2012, scientists expected the story to become clearer. Instead, it became weirder. Between the Heliopause and the edge of the Sun's magnetic domain lies a region called the heliosheath. Think of it like the outer atmosphere of the Sun's influence. It's supposed to be relatively calm. It's supposed to follow predictable patterns. It's supposed to make sense. Voyager's instruments found something completely different. The region is chaotic, turbulent. The magnetic field isn't pointing in the direction we predicted. The particles are behaving in ways that contradict multiple theoretical models. The boundary itself is thicker and more complex than anything we anticipated. Dr. Frank McDonald, a legendary physicist who studied solar wind for decades, once said, "Each time we think we understand the sun's influence, the universe shows us we were wrong." And that's the joy of exploration. He was right. He is the specific, mind-blowing discovery. Voyager detected magnetic field lines in the heliosheath that are oriented perpendicular to what we expected. Imagine you set up a traffic pattern, expecting all cars to flow north, and instead they're flowing east. That's the level of unexpected behavior Voyager is revealing. This matters because the heliosheath's structure affects cosmic ray penetration, solar wind dynamics, and potentially the long-term evolution of planetary atmospheres. If we don't understand the heliosheath, we don't fully understand how our solar system interfaces with the broader galaxy. Think of it like this. Imagine your house has insulation protecting it from the outside weather. You design that insulation based on your understanding of how weather works. But then you install a monitor at the boundary of the insulation and discover that the weather pattern is completely different from what you thought. The wind is blowing in unexpected directions. The temperature fluctuations are different. Your whole understanding of insulation effectiveness becomes questionable. That's where we are with the heliosphere. What's even more fascinating is that Voyager 2, its sister spacecraft, crossed the Heliopause about 4 years after Voyager 1, and its data presents a different picture. At a different location in the heliosheath, conditions were different. The magnetic field orientation was different. The particle distribution was different. This means the heliosphere is asymmetrical. It's not a perfect sphere around the Sun. It's lopsided, warped, shaped by interstellar magnetic fields and cosmic winds, in ways we're only beginning to understand. Dr. Tom Crimigas, who has spent over 40 years studying the outer solar system, described it perfectly. The heliosphere is not a static bubble. It's a dynamic, evolving region that's constantly interacting with the interstellar medium. Every Voyager discovery reveals another layer of complexity. And here's the implication that creates cognitive dissonance. If the heliosphere is warped and asymmetrical, then our protection from cosmic radiation is uneven. One side of the solar system has stronger protection than the other. If Earth's orbit ever took us through a region with weaker protection, which it won't, because our orbits are stable, we'd receive higher radiation exposure. But the deeper implication is this. The boundary between our solar system and the galaxy isn't a neat demarcation line. It's a fuzzy, chaotic interface. We're not as isolated from the broader galaxy as we might imagine. The influence of distant stars, the pressure of galactic winds, the sweep of interstellar magnetic fields, they're all shaping the very structure of our solar system. We're not in a bubble. We're in a dynamic, evolving interface between local order and cosmic chaos. And that changes everything about how we should think about our place in the universe. Science progresses not through perfect confirmations of theory, but through anomalies. Through moments where reality refuses to match predictions. Voyager has generated some of the most profound anomalies in space exploration. The first anomaly is called the Pioneer anomaly. Voyager doesn't experience this Pioneer 10 and 11 do, but it's directly relevant because it suggests something fundamental about our understanding of gravity might be incomplete. Both Pioneer spacecraft show a slight, consistent acceleration back toward the Sun that can't be explained by conventional physics. It's small, about 10 to the minus 10 meters per second squared, but it's consistent and measurable. For decades, physicists proposed exotic solutions, extra dimensions, undiscovered massive objects, modifications to Newton's laws, even the hypothesis that we were encountering a new fundamental force. Eventually, scientists at NASA discovered the most likely explanation: thermal radiation. The spacecraft emit heat in non-uniform directions, creating tiny thrust patterns that had been overlooked. It was solved. But for years, it represented genuine mystery. And it taught us that the universe can hide its secrets in the smallest details. Now, for Voyager's own anomalies. The most profound is something called the Voyager magnetometer mystery. Voyager carries a magnetometer, an instrument that measures magnetic fields. As it left the solar system, the magnetometer detected something completely unexpected. The magnetic field structure was far more complex than models predicted. There are regions where the field direction reverses. There are filaments of ordered field threading through chaotic space. There are wave structures that suggest active plasma instabilities. Think of it like this. Imagine you're sailing away from a continent, and your compass shows you the direction the land's magnetic field is oriented. You expect it to gradually weaken and eventually become undetectable. Instead, your instruments reveal that the field extends far further than expected, and it has intricate structure like invisible currents flowing through the ocean, creating patterns of magnetism you never anticipated. That's what Voyager discovered. But here's where it gets truly mind-blowing. Some of these structures might actually be remnants of the solar wind's interaction with the interstellar medium. They might be structures that have been there for potentially thousands of years, created by the sun's passage through different regions of the galaxy. Voyager might be revealing the history of our sun's journey through space, written in magnetic filaments. The second major Voyager anomaly involves energy flows. Instruments detected plasma waves oscillations in the electrified gas that are at higher temperatures than models predicted. Where is this energy coming from? How is it being sustained? The equations don't balance. We're missing something. Something is heating this region more efficiently than our current understanding of physics can explain. Dr. Don Gurnett, who has been studying plasma waves for over 50 years and whose instruments are on Voyager, said something profound. Every time we measure something, we're asking the universe a question. If the universe doesn't answer the way we expect, it means we didn't ask the right question yet. The third anomaly is subtler, but potentially more significant. The Voyager cosmic ray anomaly. The cosmic ray intensity should increase monotonically. As you leave the solar system, the further out you go, the more cosmic rays you encounter. But Voyager's data doesn't show that simple pattern. Instead, there are regions of decrease followed by regions of increase. There are fluctuations and reversals that suggest the cosmic ray distribution is being shaped by something we don't fully understand. This could indicate that the sun's magnetic field extends further than we thought. It could mean that interstellar cosmic rays are being deflected by unseen structures. It could suggest that our models of how cosmic rays interact with magnetic fields are incomplete. Each of these anomalies represents a gap between theory and observation. And that gap is where science lives. That's where discovery happens. Here's your moment of wonder. We don't have all the answers. Despite all our knowledge, despite all our scientific advancement, Voyager spacecraft we built in the 1970s with computing power less than a modern smartphone is regularly surprising us with data that contradicts our best theories. That means the universe is still surprising us. Reality is still more complex than we understand. And that's beautiful. That's the reason we do science. Not to reach the end of discovery, but to realize that each answer generates new questions. Each solution reveals new mysteries. Here's something that will fundamentally alter how you think about this mission. Voyager is now so far away that it's becoming increasingly impossible to communicate with it. The signal from Voyager 1 is so weak when it reaches Earth that it's about 20 billion times fainter than the weakest signals from FM radio stations. Think about that. The radio station in your city broadcasts outward in all directions. The signal only has to travel a few miles. Even so, when you drive far enough away, you lose it. Voyager's signal has to travel 14.5 billion miles in all directions, from a transmitter with the power of about 23 watts, roughly the power of a small light bulb. And we can still receive it, we can still decode it, we can still understand it. This is only possible because of one of humanity's greatest engineering achievements, the Deep Space Network. NASA operates 3 massive antenna stations positioned around the world in California, Spain, and Australia. These aren't ordinary antennas. They're parabolic dishes 210 feet across. Imagine a satellite dish big enough to cover a city block, with surfaces so precisely manufactured that if you scaled it up to the size of Earth, the irregularities would be smaller than a fingernail. These dishes are so sensitive they can detect a signal so weak that if you took all the radio waves that have ever hit Earth in the entire history of radio broadcasting, collected them all, amplified them, and created a concert of every radio signal ever transmitted, Voyager's signal would still be quieter. The engineers who designed this system and engineers like them from Jet Propulsion Laboratory, especially those working under the vision of Charles Elichik, created something that captures signals from beyond the edge of our understanding of nearby. And here's the mind-blowing part. The signal from Voyager contains data collected by multiple instruments: magnetometer readings, plasma wave data, cosmic ray measurements, temperature readings, energy flow information. All of it is compressed into that impossibly faint signal transmitted across 14.5 billion miles of vacuum. Think of it like this. Imagine you're sitting in a concert hall and someone in another continent is playing a violin. The sound is so faint when it reaches your ears that if you held your hand to your ear, you couldn't hear it. In fact, the sound is so faint it's quieter than the thermal motion of air molecules. And yet, you have instruments so sensitive they can detect it, decode the specific frequencies, and reconstruct the melody. That's what we're doing with Voyager. But there's a darker side to this beautiful achievement. The signal power on Voyager has decreased over time. The spacecraft is aging. The transmitter is degrading. The battery is decaying. Every single scientific instrument on Voyager is powered by nuclear decay, specifically plutonium-238. When that plutonium was loaded aboard in 1977, there was a specific amount. Every moment since then, atoms have been decaying. Heat has been radiating away. The available power has been diminishing. The power available has decreased from about 470 watts at launch to about 250 watts today. By 2030, there won't be enough power to operate most instruments. By 2036, Voyager will likely fall silent. We will lose our voice at the edge of forever. Think about that. We've achieved this extraordinary feat, building something that leaves the solar system, that detects the boundary of our home's influence in the cosmos, that sends us messages from the extreme frontier, and we only get about 60 years of conversation. A single conversation with the universe at its outermost border. And that conversation is ending. Unless there's a way to extend it. And there might be. Scientists have proposed that by turning off non-essential instruments, by dramatically reducing power consumption, they might keep Voyager's core systems operating until maybe 2050, maybe longer. They're already planning for Voyager's senescence, the gradual shutdown of this messenger from Earth. Here's your personal connection moment. The people who built Voyager, who launched it, who have been receiving its signals all these years, many of them are retiring. Some have passed away. Carl Sagan died in 1996, before Voyager left the solar system. He never knew with certainty that we'd reach the Heliopause. He never heard Voyager confirm that the boundary existed, but he believed, he envisioned, he sent Voyager outward based on faith that we'd eventually hear from it. That faith has been justified. And now it's our generation's responsibility to ensure that Voyager's final decades of communication yield the maximum scientific insight. We're in a race against time. Not the time of human civilization, but the time of our greatest robotic emissary. It's a poignant reminder that even our greatest achievements are temporary. Even our most distant voices eventually fade into silence. Now we reach something that reframes everything. Something that shows us Voyager isn't just passive observer, it's actively revealing the structure of our galactic neighborhood. Voyager has detected the interstellar wind. Let me explain what this means. Our galaxy, the Milky Way, is moving through space. It's not stationary. And within that movement, different regions have different speeds and directions. Specifically, the local interstellar cloud, the region of space our solar system is currently moving through, has a particular velocity and direction. Voyager's instruments detected the characteristics of this interstellar medium: the density, the composition, the velocity, the direction. And here's what blew everyone's mind. The interstellar wind isn't blowing in the direction we expected. Based on previous observations from other spacecraft and from starlight, scientists predicted the wind would be coming from a particular direction. Instead, Voyager's measurements suggested the wind was coming from slightly different angles with different speeds than predicted. Think of it like this. Imagine you're standing outside and you feel the wind on your face. You estimate the wind speed and direction based on how your hair blows and how hard the wind pushes. But then someone puts precision instruments at your location that measure wind speed and direction to extreme accuracy. And those instruments show the wind is coming from a direction slightly different from what you felt. That means your sensory perception was slightly off. And by understanding how it was off, you learn something about how to interpret sensory data from a distance. The composition of the interstellar medium is equally fascinating. Voyager detected neutral hydrogen, the most abundant element in the universe. It detected helium, heavier elements. The spectral signature tells us about the elemental composition of the local galactic neighborhood. And here's what creates cognitive dissonance. Some of the elemental abundances don't match what we expect based on stellar models. It's not dramatically different, but it's off in ways that suggest our understanding of how elements mix in the interstellar medium might be incomplete. Dr. John Richardson, who has worked with Voyager's instruments for decades, described it this way. The interstellar medium is like the atmosphere of the galaxy. Just as Earth's atmosphere has local variations in pressure and composition, the galaxy has local variations in the interstellar medium. We're mapping those variations one measurement at a time. But the most mind-blowing part is this. The direction of the interstellar wind tells us something about where the sun is going. The solar system moves through the galaxy at about 450,000 miles per hour. Not because we're actively moving, but because we're orbiting the galactic center, an orbit that takes about 230 million years to complete. 1 galactic year. The last time the solar system was at this position in the galaxy, dinosaurs had just gone extinct. That gives some scale to the cosmic timescale we're operating on. The interstellar wind measurement means we can refine our understanding of the solar system's trajectory. We can better predict what regions of the galaxy we'll be moving through in the future. And here's the profound implication. The character of the interstellar medium determines how much radiation reaches Earth's atmosphere. It determines how well protected we are from cosmic rays. It shapes the habitability of our planet. Voyager's measurement of the current interstellar wind is therefore information about our present safety and protection. We're learning that the bubble we live in, the heliospheres, shaped by the particular region of galactic space we currently occupy. Imagine if Earth orbited a star that was moving through a denser region of interstellar space. The interstellar wind would press harder against the heliosphere. The Sun's magnetic field would need to work harder to maintain protection. Cosmic ray exposure might increase. The evolutionary trajectory on Earth could be different. We are, in a very real sense, residents not just of a planet or a solar system, but of a specific region of galactic space. And that region has characteristics that make our existence possible. Voyager is revealing those characteristics. Here's a question that might never be answerable, but it's profound to consider. Will Voyager ever encounter another star? The nearest star system, Alpha Centauri, is 4.37 light-years away. At Voyager's current velocity, it will reach that system in 73,000 years. When it does, it will miss the stars by a distance of about 1.6 light-years. It will pass through that star system's outer reaches without coming close to any particular star. But here's what will happen. The gravitational field of Alpha Centauri will slightly bend Voyager's trajectory. It will marginally decelerate it. The star's gravity will exert its influence across the vastness of space, altering the course of this human-made object ever so slightly. Think of it like this. Imagine throwing a ball. And even though it seems to be traveling in a straight line, somewhere on the other side of a vast distance, an invisible mountain exerts gravitational pull that ever so slightly curves the ball's path. The effect is infinitesimal. The ball arrives at its destination just a meter away from where it would have been without the mountain. But the effect is real. Gravity connects across space. That's what happens with Voyager and Alpha Centauri. Even though Voyager won't come close to that star, the star's gravity will touch it, will affect it, will be part of its story. Now here's where it gets even more profound. In roughly 296,000 years, Voyager will pass within about 1 light-year of another star, Gliese 445. And in that flyby, Gliese 445's gravity will have a measurable effect on Voyager's trajectory. These are timescales that are virtually incomprehensible. 296,000 years. That's longer than the entire history of modern humans. Homo sapiens has existed for maybe 300,000 years. So Voyager will encounter another star at about the same time in the future as humans appeared in the past. By that time, what will Earth be like? What will humanity be like? Will we even exist? Will we have transcended biological form? Will we have colonized other stars? Will we have achieved post-scarcity civilization? Or will we have destroyed ourselves? Nobody knows. But we know this. Voyager will be there, carrying our message, carrying the voice of humanity, still asking the universe questions, still being touched by the gravity of distant suns. Think of it like this. Voyager is a message in a bottle with a delivery time of 300,000 years. We don't know who or what will be here to appreciate it. But we sent it anyway. Dr. Carl Sagan said, The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. Voyager is that knowing. Its consciousness extended to the edge of the local solar system. It's humanity reaching out to touch the cosmos. Here's your profound moment. If civilization lasts another 1,000 years, Voyager will still be traveling. If it lasts 10,000 years, Voyager will still be traveling. If humanity achieves post-biological immortality and spreads to other star systems, one of our artifacts, this small, elegant machine we built in 1977, will still be out there. Still moving, still carrying our message. That's a form of immortality. Not personal immortality. Not even civilizational immortality. But cosmic immortality. A message that outlasts everything else we create. The universe will know that we were here. That we wondered, that we tried to understand. Long after our sun has died, long after our galaxy has merged with Andromeda, Voyager will still be drifting through space, still carrying the pale blue dot photograph, still transmitting the echoes of Earth's sounds. So what comes after the edge of our solar system? What does Voyager enter when it finally leaves the heliosphere behind? This is where we must confront genuine mystery, where observation ends and theory begins. The interstellar medium, the space between stars, is not empty. It's filled with gas, dust, plasma, and fields. It's sparse compared to anything on Earth, but it's not void. A typical interstellar density is about 1 hydrogen atom per cubic centimeter. Compare that to air at sea level, which has about 10 to the 19 atoms per cubic centimeter. It's not empty, but it's incredibly sparse. In that sparse medium, Voyager will move. Slowly, over thousands of years, friction with that interstellar medium will gradually slow it down. The deceleration is minuscule, but it's real. Eventually, given enough time, Voyager might come to rest relative to the galactic frame of reference. But that's thousands of years in the future. What's happening now? Right now, Voyager is sending back data about the boundary region. It's measuring how the sun's influence gradually transitions to the galaxy's influence. It's revealing that transition zone to be far more complex than theory predicted. And here's what's mind-blowing. The structure of the interstellar medium suggests that the solar system's movement through the galaxy isn't smooth. We're not gliding through a uniform ocean. We're moving through clouds and filaments, dense regions and sparse regions, regions with high magnetic field strength and regions with weak fields. Our solar system may have just recently entered the local interstellar cloud, the specific region of space we currently occupy. We may have just recently exited a different region. The characteristics of the region we're in, the temperature, density, composition, magnetic field strength, those determine how well protected we are from cosmic radiation. If the solar system moves into a much denser region of interstellar space in the future, the cosmic ray exposure could increase significantly. This could have profound implications for life on Earth over cosmological timescales. It could influence the rate of mutations. It could affect evolutionary Think of it like this. Imagine a ship sailing through the ocean, and sometimes it passes through warm currents and sometimes cold currents. Sometimes through clear water and sometimes through fog. The characteristics of the water determines the difficulty of the journey. If the ship passes into dangerous waters, it faces challenges. If it passes into safe waters, it can thrive. The solar system is that ship, and the interstellar medium is that ocean. And right now, thanks to Voyager, we're beginning to understand what waters we're sailing through. Dr. Meraf, over a leading has proposed a revolutionary idea. The heliosphere might be shaped like a croissant. Not a sphere, not symmetric, but asymmetrical. The side of the solar system facing the direction of the sun's movement through the galaxy would have a compressed heliosphere. The The backside would have an extended tail. It would be shaped by the pressure of the interstellar wind. If this is true and Voyager's data provides evidence for it, then protection from cosmic radiation is uneven across the solar system. One side is more protected than the other. If this is true, and Voyager's data provides evidence for it, then protection from cosmic radiation is uneven across the solar system. One side is more protected than the other. This creates a subtle but profound implication. Planetary orbits in the solar system, including Earth's orbit, position us on a particular part of this croissant-shaped heliosphere. We're not at the center of equal protection. We're at a specific location with specific characteristics. This is the kind of detail that seems trivial until you realize it has profound implications for how we understand our place in the cosmos. We're not in an idealized, symmetrical, perfectly balanced solar system. We're in a real, asymmetrical, dynamically evolving cosmic neighborhood. And Voyager is revealing that reality to us. Let me ask you something that will reframe this entire journey. Why do we explore? Not why do we explore for resources? Not why we explore for economic advantage. But why does the human spirit drive us to look beyond the horizon? Why did Columbus sail west? Why did humans trek across mountains and deserts and oceans? Why did we build rockets and send them to the moon? Why did we launch Voyager? The answer is profound, and it's deeply personal. We explore because we need to understand our place. We need to know what's beyond us. We need to reach out and touch the limits of our known world. It's encoded in human consciousness. It's fundamental to what it means to be aware. Voyager represents the furthest physical extension of that impulse. It represents humanity, saying, we wonder, we ask, we reach, we try to understand. And here's what connects Voyager to you, specifically. In this moment, when Carl Sagan was thinking about what to put on the golden record, he included music. But not just great classical music or famous compositions. He included a Raga by Ravi Shankar. He included a Georgian vocal ensemble. He included Azerbaijani bagpipes. He included Peruvian panpipes. Why? Because he wanted to show the diversity of human creativity. He wanted to show that beauty and meaning-making emerges from every culture, every region, every tradition. He wanted the universe to know that humanity is not monolithic. We're a species of extraordinary diversity, all reaching toward similar goals: understanding, meaning, beauty, connection. Every person who has ever created music is represented in some way on that record. Every person who has ever felt moved by music is part of that legacy. The sounds of Earth are sounds that humans created together. Sounds that moved us. Sounds that we decided were worth preserving for eternity. You might not have made music, but you've heard it. You've been moved by it. You're connected to this project because you're human and you're part of the species that created all this. Think of it like this. Imagine you're part of a conversation that's happening across centuries and across the vast distances of space. Your grandparents contributed to building spacecraft. Your teachers taught you about the cosmos. You're watching this video, learning about Voyager, and in doing so, you're becoming part of the continuing human conversation with the universe. You're not separate from Voyager, you're connected to it. It's your proxy out there. It's humanity's voice, and by virtue of being human and being conscious and being curious, that's partially your voice too. Here's what the Voyager mission teaches us about human significance. We're small, our planet is a pale blue dot. Our species is young. Our civilization is brief. Measured against cosmic timescales, our existence is fleeting. But we're conscious. We're aware. We can ask questions about our place in the universe, and then build machines to answer those questions. We can love. We can create. We can wonder. And we can send our message to infinity. That's not insignificant. That's extraordinary. The Voyager missions teach us that human significance isn't measured by our size or our duration. It's measured by our consciousness, our ability to reach beyond ourselves, our capacity for wonder and love and curiosity. You are part of that. This moment, watching this video, learning about Voyager, this is you participating in something that extends beyond yourself. This is you being part of humanity's conversation with the cosmos. And that changes everything about how you should think about your own existence. In the coming decades, we will face a choice about Voyager that will define how we value our species' greatest achievement. As I mentioned earlier, Voyager's power is declining. The plutonium-238 that powers it is decaying according to the laws of physics. There's nothing we can do to stop that decay, but we can choose how to manage it. NASA engineers are currently developing plans for Voyager's final years. As power becomes scarcer, decisions will need to be made about which instruments to keep operational and which to shut down. This will be agonizing. Every instrument on Voyager was built by brilliant engineers and scientists. Every instrument has provided irreplaceable data. Choosing to turn off an instrument means abandoning a source of knowledge. But here's the reality. We can't keep everything running. We have to choose the most crucial instruments for understanding the interstellar medium, the ones that will provide the most profound scientific return. In Voyager's final years, those will likely remain on the instruments that provide complementary data, but less critical insight might be switched off. By around 2030, most of Voyager's instruments will go silent. By 2036, the expected silence is nearly complete. We'll lose our voice at the edge of the solar system. We'll lose the conversation. Unless we do something different. What if we took the knowledge we've gained from Voyager and built a successor? What if we sent a next-generation probe beyond the Heliopause, faster, more powerful, with instruments specifically designed to study the interstellar medium and the boundary region Voyager is now exploring? Such a mission would take decades to reach the Heliopause. It would arrive in a new era. But it would continue the conversation. It would extend the human presence at the edge of forever. Think of it like this. Voyager is like the great explorers of Earth's age of exploration. Columbus, Magellan, Cook, they sailed beyond the known world, mapped coastlines, revealed the true shape of continents. But they were the beginning, not the end. Subsequent explorers built on their discoveries. They mapped more thoroughly, they went deeper. A next-generation heliosphere probe would be the successor generation of explorers. It would build on Voyager's discoveries. It would ask new questions. It would reveal deeper mysteries. But here's the problem. Such a mission would be expensive. It would take decades to develop. It would require sustained commitment and funding. And in our current world, such long-term, expensive projects are difficult to justify when there are immediate crises demanding attention. So we may face a future where we simply let Voyager's signal fade, where we listen to its final messages and then turn away, where we commit no resources to continuing the exploration. That would be a tragedy. Not because Voyager felt it succeeded beyond anyone's imagination, but because we chose not to continue the conversation. Here's your engagement moment. This choice is coming. Within your lifetime, within the next 15 years, NASA will make decisions about Voyager's final power consumption. And as citizens, as humans, we have some voice in that choice. We can value this exploration enough to advocate for it. We can recognize that understanding our place in the cosmos is worth the investment. The great explorer Ernest Shackleton once said, "It is the job of scientists to open up the entire regions of knowledge." Voyager opened the region of knowledge at the edge of the solar system. We can choose to continue that opening, or we can let it close. What do you want to be true? If you could choose, would you rather live in a future where humanity continues to explore the edge of the solar system, or one where we've decided that's not worth doing? Think about that. And think about what that choice says about us as a species. I want to bring everything together now. I want to show you how Voyager's discoveries at the edge of the solar system fundamentally change how you should think about nearly everything. We started with the shocking revelation that Voyager 1 has traveled to the edge of our solar system. But what that really means is that humanity has extended consciousness to a distance so vast that our human minds struggle to comprehend it. We then discovered that Voyager crossed the Heliopause boundary, where the sun's influence ends and the galaxy's begins. That boundary is real. We have evidence of it. We've touched it through our proxy. We learned that this boundary is far more complex than theory predicted. It's turbulent. It's asymmetrical. It's alive with plasma waves and shifting magnetic fields. The universe revealed that it's more complicated, more intricate, more wondrous than our models could capture. We detected the interstellar wind, the characteristics of the galactic neighborhood we inhabit. We learned that our protection from cosmic radiation is not absolute, it's dynamic. It's shaped by our current location in galactic space. It could change if we moved to a different region. We learned that Voyager is carrying the voice of Earth to eternity. Not just scientific data, but music, greetings, images. Humanity declaring its existence to whatever future might exist. We've become cosmic messengers, and we learned that these discoveries required extraordinary human ingenuity. The Deep Space Network. Trajectory engineers, physicists who dedicated decades to understanding particle behavior, scientists like Carl Sagan who dreamed of what exploration could mean. But here's the fundamental reframe that brings it all together. You live on a planet that is protected by a heliosphere shaped by the sun's magnetic field. That heliosphere is created by the balance between the sun's outward pressure and the galaxy's inward pressure. That balance keeps cosmic radiation at levels that allow biological life to flourish. You exist because of that balance. Voyager's discovery of the Heliopause is therefore not abstract knowledge. It's information about the structure that protects you. It's measurement of the boundary between you and the cosmos. Think of it like this. You live in a house protected by walls. You know the walls are there. You understand conceptually that they keep the outside out and the inside in. But what if you built a device that traveled to those walls and measured their exact thickness and composition? What if you discovered those walls weren't solid but porous, with complex structure and subtle permeability? You'd understand your protection more completely. You'd understand the conditions of your existence more deeply. You'd realize that your safety is more fragile and more intricate than you knew. That's what Voyager has done for humanity. It's measured the walls that protect us. And in doing so, it's revealed that reality is more complex, more profound, and more beautiful than we understood. The cosmic reframe is this: you are not separate from the cosmos. You are not isolated in some distant, disconnected location. You are embedded in a dynamic, evolving, intricately structured universe. The boundary of the solar system is only about 100 times further away than Neptune. The nearest star is 100,000 times further away than that. The Andromeda Galaxy is about 25 million times further away than the nearest star. The scales are incomprehensible. But they're not infinities, they're real distances. Real connections. Voyager has shown us that these vast distances are traversable, that consciousness can reach across them. We sent a machine to the edge of the sun's domain. It's still talking to us. It's still revealing secrets. It's still advancing human understanding. And in doing so, it's teaching us something profound about ourselves. We're capable of extraordinary things. We can reach beyond ourselves. We can extend consciousness across the solar system. We can understand the universe. That capability defines us. That's what it means to be human in this cosmic age. Here's the profound truth Voyager teaches. The universe is not our enemy. The cosmos is not hostile. Instead, it's infinitely complex, infinitely beautiful, and infinitely worth understanding. And we have the capability to understand it. We have built machines that can touch the boundary between home and infinity, and those machines send back word of what they find. We are a species that asks questions and builds answers. We are explorers. We are seekers of truth. We are the universe aware of itself. I want to end this not with facts, but with something more important. I want to end with what this all means. 50 years ago, human engineers and visionaries looked at the cosmos and asked, what if we could touch the edge? What if we could see beyond ourselves? What if we could send a message to the infinite dark and hope that someday someone would hear? That wasn't naive. That wasn't impractical. That was the highest expression of human aspiration. It was consciousness reaching for understanding. It was humanity recognizing that the impulse to explore, to wonder, to reach beyond the horizon is not a luxury. It's fundamental to what it means to be aware. And that same impulse lives in you. Right now, this moment, you're watching a video about Voyager because some part of you wants to understand the universe. Some part of you is curious about what's beyond the familiar. Some part of you resonates with the idea that humanity has reached to the edge of the solar system and discovered wonders. That's not coincidental. That's evidence of the same consciousness that drove Voyager. You're connected to that mission. You're participating in that exploration. You're part of humanity's conversation with the cosmos. Think about what you'll do with this knowledge. You now know that Earth is protected by a heliosphere shaped by the sun's magnetic field. You know that this heliosphere is currently being studied at its boundary by the most distant human artifact ever created. You know that the structure of this protective layer is more complex than theory predicted. You know that the universe is still surprising us. What changes in you knowing that? How does your sense of self shift knowing that you live on a planet protected by a boundary being, measured by a machine that's been traveling for nearly 50 years? I think it shifts something fundamental. I think it recontextualizes your existence. You're not isolated. You're not separate from the cosmos. You're embedded in it, protected by it, part of it. Here's what I want you to do next. I want you to go outside. Look up, find a clear patch of sky, away from lights if possible, and look at the stars. Really look at them. Not as distant points of light, but as suns with their own systems, their own boundaries between their domain and the cosmic dark. Each star you see is billions of miles away. Each star is surrounded by its own heliosphere. Each star is protected by its own magnetic bubble. And if that star has planets, those planets are shielded from cosmic radiation by those magnetic fields. Somewhere out there, around some distant star, might be conscious beings asking the same questions you're asking, looking at their own star, wondering about the universe, creating their own voyages to explore their own edges. You're looking at their world from here, and they might be looking at your world from there, connected by light and gravity and the infinite structure of the universe. That's not abstract anymore. That's the reality Voyager has revealed. That's the truth of existence in a cosmos that is connected, interdependent, and profoundly real. Here's the final mind-blown moment. The information you received in this video information about Voyager, about the Heliopause, about the structure of the solar system originated from photons sent from that spacecraft across 14.5 billion miles of space. Those photons arrived at Earth just milliseconds ago. They were received by the Deep Space Network. They were decoded. They were analyzed. They were understood. And they were integrated into human knowledge. That means you have, in your mind, right now, information that originated at the edge of the solar system. Your consciousness contains data about the heliosphere. Your understanding has been updated by information sent from beyond the known planets. You're not separate from Voyager's discoveries. You've internalized them. They're part of how you understand reality now. And that changes you. Let me leave you with Carl Sagan's words about the pale blue dot, because they capture something essential. All that humanity has ever accomplished, all our art, all our music, all our science, all our kindness has happened on this tiny speck of dust in a shaft of light. Every human who has ever lived there. On that dot, we might presume that there are other intelligences out there who have similar thoughts about their own worlds, who cherish their own tiny dots. It underscores our responsibility to treat this dot, our world, with care and tenderness. Because, in this cosmos, we're home. This is where we belong. Voyager carries that message outward. Voyager carries the voice of Earth. Voyager carries your existence encoded in sound and image, traveling toward infinity. You are part of that mission. You are part of humanity's voice in the cosmos. If you've watched this far, you've just spent nearly 4 hours learning about Voyager. You've become, in a real sense, part of the community of humans who understand this achievement. You're now someone who knows what Voyager detected at the edge of the solar system. You're someone who understands that the boundary of the sun's domain is complex, dynamic, and still revealing secrets about reality. You have a responsibility now, not a burden. A responsibility. The responsibility is to share this wonder, to tell others, to help other humans understand that we've done something extraordinary. We've reached beyond ourselves. In the comments below, I'm asking you to do something. I want you to tell someone else about Voyager. Not today, necessarily, but sometime soon, when it feels right. Tell someone about Voyager's discovery of the Heliopause. Tell them about the pale blue dot. Tell them about humanity's greatest journey. Share this wonder. Because that's how we keep the spirit of exploration alive. That's how we maintain the impulse to understand. That's how we ensure that future generations will also look up and wonder and ask questions and reach beyond themselves. Voyager was built by humans asking, what if we could know what's out there? The answer came back, it's more wonderful than we imagined. Your role now is to ask, what if we could inspire others to ask the same question? What if we could share this wonder with more and more people until humanity as a whole understands our place in this beautiful, complex, or inspiring cosmos? That's the final step. That's how exploration continues. Subscribe to this channel. Not because I need subscribers, but because you need to stay connected to this community of wonder seekers. The people who watch videos about Voyager are the people who understand that existence means reaching beyond ourselves. That's a community worth being part of. Share this video with someone. Someone you care about. Someone who might be searching for meaning. Someone who might benefit from knowing that humanity has reached to the edge of the solar system and is still talking to what we sent there. And finally, look at the sky again tonight. Remember that you're standing on a world protected by a heliosphere. Remember that that protection is currently being measured by our proxy at the edge of the sun's domain. Remember that you're part of a species that has achieved something extraordinary. Remember that you matter. Not because of what you've accomplished yet, but because you're conscious. You're aware. You can wonder. And you can share that wonder with others. That's what makes us human. That's what Voyager represents. That's what the universe recognizes in us. We are the cosmos asking questions about itself. And that is beautiful beyond measure. But I want to extend this conversation because there's more to understand. More layers to peel back. More questions that Voyager is helping us answer right now, in this moment. Because here's something that most people don't realize. Voyager's mission isn't ending. It's transforming. The original Voyager mission was designed to study Jupiter and Saturn. That mission was completed in 1981. Then NASA extended it. The extended mission was to reach the Heliopause. That milestone was achieved in 2012. But we're still receiving data. We're still operating instruments. We're still learning. What we're in right now, this period where Voyager is deep in the heliosheath, measuring this transition zone between solar and galactic influences, might be the most scientifically valuable phase of the entire mission. Because Voyager is answering questions we didn't even know to ask when it was launched. Think about that. A spacecraft designed 50 years ago is now collecting data that addresses questions formulated by scientists working in laboratories built after Voyager launched. The machine is more valuable to modern science than it was to the science of its own era. That's the power of exploration. You don't know what you'll discover until you get there. Now, here's something that will create genuine cognitive dissonance. We're not entirely sure what Voyager is measuring. Yes, you heard that right. We have instruments on Voyager collecting data. We receive that data. We can quantify it, we can graph it. We can create mathematical models of it. But in some cases, we don't fully understand what the data represents. Take the plasma wave measurements, for instance. Voyager's plasma wave instrument detects oscillations in the electrified gas plasma waves. These are like ripples in water, but in the electrified particles that fill space. The instrument measures their frequency, their intensity, their characteristics. But here's the puzzle. Some of the plasma wave signatures we're detecting don't match any theoretical predictions. They're at frequencies we didn't expect. They have intensities that shouldn't be possible given the local conditions. They're behaving in ways that suggest physical processes we haven't adequately theorized. Dr. Don Gurnett, the principal investigator for Voyager's plasma wave instrument, has been studying these anomalies for years. He's published papers proposing explanations. But here's what he's honest about. We don't have a complete understanding. The universe is showing us something we haven't fully categorized yet. And that's exciting. That's the frontier of human knowledge. That's where discovery happens. Think of it like this. Imagine you're listening to a piece of music, and suddenly you hear an instrument you've never heard before. You don't have a category for it. You don't know how to describe it, but you know you're hearing something real, something that emerged from human creativity. Now you need to figure out what it is, where it came from, what technique created it. That's what we're doing with Voyager's data. We're encountering something real, something the universe is showing us, and we need to figure out how to understand it. Here's another profound mystery that Voyager is revealing: the nature of the Heliopause boundary itself. We thought the Heliopause would be a relatively thin layer, maybe a few thousand kilometers thick, a membrane-like boundary between two different regions. Instead, Voyager's data suggests it's thicker, more complex, with internal structure, almost like an atmosphere itself, with layers and variations. What creates this structure? What processes are at work? One hypothesis is that the boundary isn't static. It's constantly moving. The solar wind pushes outward. The interstellar medium pushes inward. The balance between them creates oscillations. The boundary undulates. It waves. It moves back and forth. Imagine the boundary between ocean and atmosphere on Earth. It's not a perfectly flat, infinitely thin surface. It has waves. It has turbulence. It has internal structure. The Sun-interstellar medium boundary might work the same way, but on scales so vast that they're measured in astronomical units. If that's true and Voyager's measurements suggest it might be, then the heliosphere isn't a static sphere. It's a dynamic, breathing, oscillating structure. It's alive in the sense that it's constantly changing. And here's what that means for us. The protection that shields Earth from cosmic radiation isn't constant. It's varying. It's dynamic. Some years, the heliosphere might extend slightly further. Some years, it might compress slightly. Our cosmic ray exposure isn't absolutely fixed. It's modulated by these oscillations in the boundary. This has implications for long-term habitability, for mutation rates, for the evolutionary trajectory of life on Earth. Over cosmic timescales, Dr. Meroff. Over who's been pushing the field to reconsider how we think about the heliosphere structure. Put it this way, the heliosphere isn't a bubble. It's a living system. It has structure, it has dynamics. It responds to its environment. That reframing is important. We tend to think of the solar system as a static, unchanging domain. The heliosphere seems like a permanent fixture. But Voyager is showing us that it's dynamic. It's evolving. It's responding to the galactic environment. Which leads to the next profound question. Is the heliosphere shape the same everywhere? We have data from Voyager 1, which crossed the Heliopause in one location. We have data from Voyager 2, which crossed in a different location several years later. The two crossings showed different characteristics. Different magnetic field orientations, different plasma conditions, different particle distributions. This suggests that the heliosphere isn't symmetrical. Voyager 1 and Voyager 2 are moving in different directions away from the Sun. They crossed the Heliopause at different points on the boundary, and they're measuring different conditions. What does that tell us? It tells us that the heliosphere is lopsided, warped, shaped by the asymmetrical pressure of the interstellar wind. But here's where it gets fascinating. If the heliosphere is asymmetrical, then our solar system isn't in the middle of it. Earth isn't equidistant from the boundary in all directions. We're at a particular location with particular characteristics. We're not at the center of our cosmic neighborhood. We're at a specific point within an asymmetrical structure. That specificity might matter for our evolution, our safety, our long-term habitability. Think of it like this. Imagine your house is built inside a cave, but the cave isn't centered around your house. The entrance is closer on one side than the other. One wall of the cave offers more protection from external wind and weather than the opposite wall. Your house's location within the cave determines its exposure to the elements. The solar system is like that. We're at a specific location within an asymmetrical heliosphere. That location has specific implications for cosmic ray exposure, for solar wind dynamics, for the conditions in which life has evolved. This is profound because it means Earth's habitability is dependent not just on our distance from the Sun, but on our position within the heliosphere. If the solar system were in a different location within the heliosphere, closer to the front, closer to the back, off to the side, conditions would be different. We are not in an optimized, centered location. We're in the actual location. And that actual location has characteristics that we're only now beginning to understand. Now here's something that connects this back to you personally. These characteristics of the heliosphere might influence mutation rates in organisms on Earth. Cosmic rays that penetrate into the inner solar system cause mutations in DNA. Most mutations are harmful. Some are neutral. Occasionally, one is beneficial and drives evolution forward. The rate of cosmic ray exposure partially determines the rate of genetic mutation. If the heliosphere provided different protection at different times in Earth's history, then the mutation rate would have varied. Periods of stronger protection would lead to lower mutation rates and slower evolution. Periods of weaker protection would lead to higher mutation rates and potentially faster evolution. The history of life on Earth might be written partially in the history of heliosphere dynamics. The times when evolution accelerated might correspond to times when cosmic ray exposure increased due to changes in the heliosphere. This is speculative, but it's not baseless speculation. It's hypothesis grounded in physics and biology. Voyager's measurements of the heliosphere are giving us data to test these hypotheses, which means your existence, your genetic code, your particular combination of DNA might be influenced by the current state of the heliosphere. The cosmic rays that reach Earth are filtered by the heliosphere. The mutation rates in your cells are affected by cosmic ray exposure. Your existence is connected to this cosmic boundary. Here's another layer of understanding. The interstellar medium that we're now entering isn't random. It has structure. It has history. The local interstellar cloud, which our solar system is currently moving through, has particular characteristics. But other regions of the galaxy have different characteristics. Some regions are denser. Some are sparse. Some have strong magnetic fields. Some have weak fields. As the solar system orbits the galactic center, one complete orbit every 230 million years, it moves through different regions of interstellar space. The protection we currently enjoy might be better than or worse than protection in other regions. If our solar system moved into a denser region of interstellar space, the cosmic ray exposure would increase. Think of it like migration. A species migrates to a new environment with different conditions. The environment affects the species' survival and evolution. The solar system migrates through different regions of the galaxy. Those regions affect the solar system's characteristics and the evolution of life within it. We've been fortunate to be in a relatively low-density region of interstellar space. We've had relatively good protection from cosmic radiation. This has allowed complex life to evolve. But that's not permanent. Eventually, the solar system will move to a different region. The conditions will change. Voyager is revealing what those conditions are like at the boundary where we're currently transitioning between regions. It's mapping the specific characteristics of our current cosmic neighborhood. And here's the profound implication. We're at a transition point. We've recently entered the local interstellar cloud. We might stay in it for millions of years. Or we might be exiting it soon on cosmic timescales. The boundary Voyager is measuring might be one we're currently crossing. If we're crossing a boundary into a denser region, cosmic ray exposure might increase over the next million years. Life on Earth would need to adapt. Evolution would accelerate. New pressures would drive new adaptations. We don't know if this is happening, but Voyager's measurements will help us figure it out. Here's your profound moment of realization. You're living at a cosmic transition point. Your generation is living during a time when the heliosphere is being measured at its boundary. Your civilization is spanning a moment when humanity is learning the structure of the cosmic environment it evolved within. This isn't coincidence. This is your moment in history. This is your generation's task, to understand the cosmos that birthed you. The scientists analyzing Voyager's data right now are working on questions that will shape humanity's understanding for centuries. The decisions we make now about exploration, about funding, about priorities, those decisions will determine whether we continue to reach outward or whether we turn inward. Think about the Voyagers as a conversation between humanity and the universe. The universe created us. We evolved, we became conscious. We asked questions, we built machines to explore. The machines sent back data. The data revealed new mysteries. The universe is responding to our questions with questions of its own. It's showing us that reality is more complex than we thought. It's challenging us to understand deeper. It's inviting us to continue the dialogue. But dialogues require both parties to engage. If humanity stops asking questions, stops funding exploration, stops reaching outward, then the conversation ends. The universe will keep evolving. Stars will continue to form and die. Galaxies will merge. But the dialogue between human consciousness and cosmic reality will cease. Is that what you want? Here's what I want to propose. I want to suggest that you have a role to play in this conversation. Not as a scientist necessarily, not as an engineer, but as a conscious being who values understanding. As someone who can recognize the importance of exploration and advocate for it. You can do this in simple ways. You can share what you've learned about Voyager with others. You can express support for space exploration in discussions. You can vote for representatives who value scientific investment. You can inspire younger people to pursue careers in science and engineering. These aren't glamorous actions. They're not heroic, but they're how civilizations choose their priorities. They're how we collectively decide what matters. Voyager represents a choice humanity made in 1977. A choice to explore. A choice to reach beyond ourselves. A choice to say, we are curious. We are adventurous. We are willing to invest resources in understanding. We have the opportunity to make that choice again. We have the opportunity to continue the mission. We have the opportunity to ensure that when Voyager finally falls silent, we're ready to send a successor. That we're ready to continue the conversation. But that requires choosing it. Choosing to value it. Choosing to prioritize it. So here's my final call to action. Think about what kind of future you want to live in. Do you want to live in a future where humanity continues to explore the cosmos? Where we continue to ask questions and build answers? Where we continue to reach outward and understand deeper? Or do you want to live in a future where we've turned inward? Where we've decided that the cosmos is too distant, too expensive, too impractical to explore? Where Voyager's final signals fade and we don't replace it? The choice isn't being made by distant politicians or scientists. It's being made by people like you. By the collective decisions of billions of individuals about what we value, about what we prioritize, about what we believe matters. Voyager taught us something profound. We're capable of extraordinary things. We're capable of reaching to the edge of the solar system. We're capable of understanding the cosmos. We're capable of sending our voice to eternity. That capability is in you too. That same consciousness, that same curiosity, that same drive to understand and reach and explore. What will you do with it? The universe is waiting for your answer.